Hello, welcome to La Excellence. Welcome to Science and Technology series. We are discussing certain important concepts with regard to science and technology, and today's concept is nuclear energy technology. Let us understand what are the different ways of generating energy using nuclear material, what India is using, out of which what we have, what are our policies, what are the constraints, all these issues with regard to nuclear energy, let us now try to understand. First of all, let us understand what is the meaning of nuclear energy. We know that atoms carry certain energy. They have nucleus, electrons, protons, all these. So they carry certain form of energy. And this energy can be obtained in two ways. One, by merging two atoms, or by dividing one bigger atom into multiple smaller atoms. That's why this is called nuclear energy. We are obtaining this energy from the nuclear reactions through these atoms. It can be division like this, fission. Fission is division, or fusion means combination. We can divide a bigger atom into multiple lighter elements, or we can combine smaller atoms into bigger element. Two ways of generating nuclear energy. Now let's see how this energy is generated, how this one is generated, which one is more easier to generate. Okay, the first and important form of nuclear energy is fission energy. Fission means division energy. A bigger atom divides into smaller elements. As a byproduct, it releases energy. Our requirement is this. We use this energy to heat up the water, and this heated water turns the turbines. These turbines they generate the electricity. We want it ultimately to produce the energy, that is electricity. So this energy in the form of heat is obtained from the nuclear reactor, and then we use water. So water absorbs the heat and then turns into steam. This turned steam turns the turbines. Turbines generate the electricity. Fission reaction in general happens in the nuclear fissile material. Fissile means which can divide. This is a nuclear material. The most used one is uranium 235. This is one of the radioactive material which is highly fissile, so we use this material. But in India, the problem is we have certain uranium reserves, but then we don't have sufficient reserves to maintain the nuclear power plants in India. But we have another form of nuclear material, that is thorium. India has largest reserves of thorium in the entire world. 25% of reserves of thorium are located in India. But then the problem is thorium cannot be used directly in this nuclear energy generation. So we have a problem. We have certain reserves, uranium reserves, but these are not sufficient. Okay. So fission is this one. And where does this happen? How it happens? Let us understand. This is a typical nuclear power plant disectional diagram. Here if we see, this is nuclear reactor. This is nuclear reactor. This nuclear reactor outer wall is built with concrete. So this is a containment structure built with concrete. Okay. Inside this we have core. We have certain devices. If you look at here, we have core. Core means here we place the nuclear material. All this uranium is placed in the form of rods. Okay, this also we understood. And then this is a device into which there are certain control rods. What are these control rods? Control rods, they control the fission reaction, because every time one bigger uranium disintegrates, it leads to three more neutrons and then plutonium, the other lighter element, plutonium. So these three again they react with uranium, again they release three neutrons, 3 3. So this is called chain reaction. We should control this chain reaction, otherwise it leads to excessive generation of heat. So generally we have control rods to control the chain reaction that happens in the nuclear reactor. Okay, that's why we place control rods. Pressure vessel. This vessel can hold the pressure within this. And we pump the water into this. We pump the water, cooler water. And this water, when it goes into this chamber, it gets heated up because of this nuclear reaction. So this heated water goes into this. The steam goes through this particular pipe and it turns this turbine. It generates the electricity. And then we have water. We said we need water. So water is pumped into this. So continuous supply of water is needed. That's why we take water from a lake or a river or nearby ocean. We take the water and we supply it to the nuclear power plant. This is the typical structure of fission reactor. Fission means division. Fission nuclear reactor. Look at this map. These are the areas where we have functional nuclear power plants. Kudamkulam Atomic Nuclear Power Plant, Madras Atomic Power Plant, Kaiga Generating Station, Tarapur in Maharashtra, Kakrapar in Gujarat, Rajasthan Atomic Power Station in Rajasthan, Narora Atomic Power Station in UP. These are the areas where we have functional nuclear power plants. In the last few years, government also proposed certain new nuclear power plants in various places. One is in Kovada. Kovada is in AP. Kovada. In West Bengal, this place called Haripur. And we have four more nuclear power plants, four more nuclear reactors proposed in Kudamkulam. Already two phases are on, they are functioning, and four more we have proposed. In Kaiga, we have proposed two more nuclear reactors. Jaitapur in Maharashtra is a new place, so where we propose the new nuclear power plant. Next, this one, Mithi Vidhi is another place in Gujarat. Government has proposed a nuclear power plant over there. And then look at here, this one, Bhimpur. Bhimpur is proposed Chukta in Madhya Pradesh, Mahi Banswara in Rajasthan, Gorakhpur in Haryana. These are the areas where we propose the new nuclear power plants. But as we know, nuclear power is very risky. Nuclear power generation is very risky. It can lead to accidents. That's why many people are resisting these nuclear power plants. Plus, we also know that we don't have enough resources of uranium. We have thorium, but we don't have enough resources for uranium. So the government thought that instead of using uranium, why can't we use thorium? Why can't we have a process wherein we can generate the power, nuclear power, using thorium itself? Then, not now, in 1950s, our government has thought about three-stage nuclear power program for India. Let's understand what is it. India's three-stage nuclear power program. In stage 1, we are going to use uranium. Yes, we are going to import it or we are going to use whatever is locally available. Uranium 235 we are going to use, and we are going to have pressurized heavy water reactors. Pressurized heavy water reactors. When we discussed the fission nuclear reactor, we understood that there is a pressure chamber, right? So, in this pressure chamber, we use heavy water that is called D2O. D2O as a moderator. It reduces the temperatures in the pressure chamber. That's why it is called pressurized heavy water reactor. First stage, we use that. And we know that when we use uranium 235, we are going to get lighter material called plutonium. Plutonium is the byproduct. So in the second stage, what we are going to do is, anyway, we know that we don't have enough uranium. So we are going to combine plutonium with uranium. We are going to use this part of uranium, part plutonium, and we are going to have this fast breeder reactor. Fast breeder reactor. Fast breeder reactor means here we don't use any control rods. We don't control the neutrons. Breeder means we are using raw material plutonium and it also leads to the end material called plutonium. So it breeds its own raw material. So that's why it is called fast breeder reactor. And then in the third stage, we are going to use certain amount of uranium and we are going to develop it using thorium. That means we take thorium, we said we have largest amount of reserves, and this thorium is processed thorium is converted into uranium, and then we are going to use it in the breeder reactor. So first stage of India's nuclear power program is this one, pressurized heavy water reactor. Second stage is FBR, fast breeder reactor. Third stage is breeder reactor. We and Russia, India and Russia are the major countries who are operating fast breeder reactors. Other countries are going for pressurized heavy water reactors only. And we have one nuclear power plant running with thorium. This is in Gujarat called Kakrapar. Kakrapar is the only operational thorium reactor in the world. In other countries, we have thorium reactors, but they are experimental. We have operational, that means which are running. So here also we have depicted the same process over here. In stage 1, we are going to use natural uranium, pressurized heavy water reactors, and then we are going to generate electricity. In stage 2, plutonium is used. Again, plutonium is the byproduct. So it breeds plutonium. In stage 3, we are going to take uranium 233 enriched from thorium. This uranium 3 fueled breeders are used. Again, we get uranium. That's why it is called breeder reactor. In each stage, we can generate the electricity, and we are using the end material of each stage as the raw material for the further stages. That's why this is very, very important. This we proposed under Homi Bhabha. He was one of the pioneers in India's nuclear power program. The next type of nuclear energy is fusion energy. Fusion means combination. In our solar system, sun uses this fusion form of energy. Hydrogen and hydrogen atom, these two are fused, and then it leads to formation of helium plus energy. So here energy can be used to generate the electricity. That's our motto. So fusion reactors, how these fusion reactors work? See, in general, whatever nuclear reactors that are operational in the entire world, not just in India, in the entire world, they all are fission. Fission means they all are working based on the principle called fission reaction. Because fission reaction is very easy to start, easy to store also. So that's why we are going for fission reaction. But fusion is important because we have, let's take this case, do we have hydrogen abundant in the atmosphere? Yes. But do we have uranium abundant in the atmosphere? No. So this one is freely available, and the energy generated can power us for many, many years with very less radioactivity. Here, radioactivity is huge. Here, radioactivity is less. So, we have, yes, clear advantages of using fusion energy. But what is the difficulty? Why most of our nuclear power plants are using fission technology? Because fusion or fusing these two atoms together takes a lot of energy. That's why it is very difficult. Let's take this one, thermonuclear reactor. We have a particular experimental reactor called International Thermonuclear Energy. This is also called ITER, International Thermonuclear Energy Reactor. This is placed in France. We all countries are funding it. India is also funding it. There we have developed a nuclear reactor called Tokamak. These are reactors where we have larger magnets placed. See, consider this one. This thing is a magnet. This side, this is a magnet. These magnets, why are we using magnets? Here we just used a concrete shield and a silver can. Why are we using this tokamak where we have larger magnets? Because we just said that it requires lot of energy. This energy is up to 100 million degree Celsius. At this high temperature, the electrons that are revolving around the nucleus, they come out of it, they disjoin. So the matter won't be in the form of solid, in the form of liquid, in the form of gas. No. The matter will convert itself into plasma. So plasma cannot be held at this temperatures in any of the existing physical materials. But to generate the electricity, we should hold the matter at one place. That's why we are using high energy magnets. These magnets, they hold this particular plasma for a longer period of time. If they hold this particular thing, what happens? Let's see. Here, hydrogen molecules are placed at this high temperatures. We provide this high temperature. At this high temperature, the matter, the gas, hydrogen gas converts into plasma. This plasma is heated continuously at this temperature, and this matter is held with the magnets, high and powerful magnets. This generates electricity. Helium pipe, this one, through that helium goes out and then it generates heat. This heat is used to heat up this water and it generates the steam. Steam turns the turbines turn, and then it generates the electricity. Is this good? Yes, it's good. But as we just discussed, there is no physical material on this earth present which can physically hold this particular matter at this high temperatures. So we are using magnets. Okay. Are we producing electricity using fusion process? Yes, we are producing, but all of them are at experimental stages. Experimental stages. Only this one, ITER, this is a research facility in France where many countries are participating. This one, the experiments are going on really ahead. In other countries, all the experiments are at the initial stages. This one, ITER. Initially, it was called as International Thermonuclear Energy Reactor, but now ITER converted into a Latin term, and that means the way. It shows us the way. That's how we put it as. In southern France, we have this nuclear facility. 35 nations are collaborating. Out of that, 7 major countries are funding. India is funding 9% of total expenditure for this ITER project. India is funding total 9% of the funding. Mostly this is through knowledge partnership. We are sending our scientists over there to work and we are giving them certain materials. That's how India is contributing to it. See this one. In 1985, this idea of fusion reactors started. China, European Union, India, Japan, Korea, Russia, United States. Korea here means South Korea. All these are participating. There are other countries also, 35 nations total. There are other countries that are collaborating scientifically, but these countries are funding also. This one is called Cryostat. Cryostat is a vacuum chamber. This one, this is a vacuum chamber. And do you know, in this entire ITER project, India has contributed to this particular one. Many contributions are there, but this is the major contribution. We have developed this cryostat, built it in India, and we have given it to ITER project. There are many scientists involved, but cryostat is one of our India's major contribution. This is the core element in the entire thermonuclear reactor. This is vacuum chamber placed in the middle of the thermonuclear reactor. And one more question, do we have our own indigenous fusion reactor? Yes, we have it. And initially, Russia developed it in 1968. After that, many countries started developing their own fusion reactors called tokamak. Tokamak is the name of this nuclear reactor where two powerful magnets are placed. In India, we have it from 1980s. We name it as Aditya. Aditya Tokamak is the name of our fusion nuclear reactor. But that's in initial stages. The significance of ITER, that is International Thermonuclear Energy Reactor, is 60% of work is over. By 2035, we are going to generate the power using this nuclear reactor. What are we going to do? We are going to supply 50 megawatts of power. For each 50 megawatts, we are going to generate 500 megawatts of power. That means the total output is 10 times of the input supply. As of now, all the nuclear fusion reactors, their net gain is zero or minus. Net gain means we said it requires lot of temperatures. So let's say if we give 10 megawatts of input, we are getting 6 megawatts of power. So what is the use of this? No use. So in this ITER, our plan is to maximize the power output to 10 times initially. So it is going to start in 2035. Okay, we understood what is nuclear energy, two types of nuclear energy, and how India is developing its own indigenous energy, all that. Good. Let's understand what are the advantages with this nuclear energy? What are the disadvantages? Okay, if there are advantages, there might be some constraints in using it. What are they? What are the government initiatives to promote nuclear energy? What is the way forward? Let's understand this. What are the advantages? Why do we use nuclear energy, by the way? Because it provides continuous supply of same quality power throughout, and it has cross sectoral use. For example, we use nuclear energy and nuclear power in defense. For example, nuclear submarines. So we have cross sectoral use, and we use it in medicine. In the field of medicine, we need nuclear processed material. And to make nuclear bombs, we need nuclear reactor. So it has cross sectoral use and it provides continuous quality supply of power. Consider solar power. Only during daytime it produces energy, but if it is nuclear, it produces continuous supply of power. What are the disadvantages? What are we going to do with the nuclear waste? We said plutonium is produced after the entire process. What are we going to do with it? Do we have safe disposal policy? No, we don't have safe disposal technique. If it is out in the atmosphere, it is going to cause nuclear damages. So that's one problem. Next, nuclear accidents or disasters. So we have many nuclear disasters accidents in the past few decades. Recent one is Fukushima. Fukushima is a place in Japan in 2011 due to a tsunami and a high intense earthquake. Fukushima nuclear reactor got damaged. It has led to huge economic as well as environmental crisis. So that nuclear reactors are prone to failures, maybe during natural disasters or due to technical failures. So that's why these are some of the disadvantages. What are the constraints? Yes, we want to use it in spite of its disadvantages, we want to use it. But do we have nuclear raw material? No, we need to import it. And land use constraints. For example, you might have observed it with regard to Kudamkulam. Kudamkulam nuclear power plant, when we wanted to get the land for it, this nuclear power plant is built by Russia, built with the help of Russia, Russian technology. So when we want to get the land, people opposed it. They said these are not good. They are going to cause harm. We are not going to give land. All that. So land use constraints are there. It requires a lot of water. There are certain constraints. Then what are the government programs? Specifically for nuclear power, we don't have any programs or policies, but for use of nuclear weapons, we have a doctrine called Nuclear Doctrine of India. So that's a different concept. Okay, what is the way forward then? We want to use nuclear energy, but what is the way forward? The way forward is to find out the safe disposal mechanisms, non proliferation techniques, because this energy, nuclear energy, and the material used can be used to develop nuclear weapons. So, non proliferation should be there, and we know that in a long term this is not sustainable, environmentally sustainable. So, we need to go for alternatives like solar, wind, and other sources of energy. This is about nuclear energy chapter. If you have any questions, queries regarding it, please ask us in the comment section. All the best. Stay focused. Thank you.